Welcome back to ECE 501B. There is the date in the upper left-hand corner. I guess it's in the lower right-hand corner for those of you really following along intently, but we're in October. We'll soon be out of October, and I thought it was a good idea to start giving you some more material, which means on course resources, which is a new module on the content page, you will find 5 new pieces of material. So while you're working homework 5, which is due this Thursday, not Halloween, that's the next day, if that means anything. Then homework 6 is due that next week because we have our second exam a week from Wednesday. Is that right on the dates? So things are building up very quickly, and we will see. Your project can be examined by looking effectively at these resources, meaning you might draw a project, an inspiration for a project from something in these course resources or something like the course resources. The course resources consist of signal theory. That's the second textbook in the class, and that's available to you now as a PDF file, and that works with the counterpart to what we've been doing all along. We're working with finite dimensional vector spaces. That is now infinite dimensional. Now we have an infinite dimensional counterpart to what we are talking about now in finite dimensions. That's then signal theory by L.E. Franks. There's a paper, the $25 billion eigenvector is a part of that title, and now you're very comfortable with eigenvalues and eigenvectors. And I went to the Google site and found how they were writing Google today. That's my mimicking of the Google. I didn't get that trademarked, so I hope they don't come after me for using their particular spelling or the way that they write it. There is a yellow O in there. It's not very visible. There's also a paper on the football ranking, and again, that uses linear algebra. That was to show how you could use some linear algebra techniques to be very much related or even competitive with the BCS formula, which no longer exists. That's why it's deleted in 2014. But that used to sort of raise a lot of eyebrows. Oh, the BCS, the Bowl Championship Series, how are you ranking football teams? Now I think they have individuals doing that now. But before, they were doing it with an algorithm or some way, and it was hard to understand. Well, this paper was written as a counter to that, saying here's a pretty easy way to rank football teams, basically just on wins and losses. And it again deals with matrices, meaning if you have, and how many teams are in that particular Division 1A set? I think it's over 100, isn't it? 120. I don't know what's Division 1A. I think it is more than that, but they don't all play themselves. So how can you now rank teams that maybe play similar teams or the same teams, but they don't all play each other, and maybe they just play a subset, which they do, but it's not the same subset? How do you rank those? That's discussed in this football ranking paper, and it is very consistent with the way that the Bowl Championship Series ranked teams, and this is all just based on wins and losses and matrices. Then there's another paper on principal component analysis, which is a tutorial paper. Has anyone heard of SVD, singular value decomposition? That's related to principal component analysis. If you now have a lot of data, how do you make sense of that data? How do you somehow figure out what's important, what's critical, what's principal with respect to that data? That's that paper. And then if you want to know all about the laws of the universe, there are 3 chapters from a book by Roger Penrose, and we may talk about a Penrose inverse. It's sort of a pseudo-inverse for matrices, but he wrote a book that the title begins, The Road to Reality, and somewhere after the colon is the laws of the universe. But that's, if you read the entire book, which is over 1,000 pages, it's trying to build up the mathematical machinery to maybe allow you to connect relativity with quantum mechanics. That hasn't yet been done, I don't believe. And now, what's the mathematical machinery for doing that? You don't have all 34 chapters, but you have the first 4 minus the introductory chapter. So in the second, third, and fourth, you start seeing this progression from the Pythagorean theorem, which we've now looked at from a more general perspective. But that's sort of where he begins this journey of the laws of the universe. And it's nice to read, and that sort of shows you or helps you understand or connects what we're doing in this class with something a little bit more out there. Quantum mechanics, relativity, making those fit together nicely. Is that possible? What mathematical machinery is available to do that? That's the beginning pieces of that 1,000 pages. This first 3 chapters that are provided here are not too difficult. So it basically goes from the Pythagorean theorem up to talking about complex numbers, but it's in an interesting fashion of discussion. Those pieces of course resources are now available on D2L, and you might start reading those and letting your sleep patterns start to figure out what it is that you might want to do for a project. Looking at those, reading the abstracts of those papers, looking at signal theory. What do you want to do for a project? And then I'll figure out what I want to assign for a project, and then we'll move forward. But that will be due near the end of the semester. But we're getting to a point where I think it's reasonable for you to now start jumping into some of this literature. Meaning today's goals, I think, will get through chapter 6. Exam 2, I'm thinking, won't cover completely all of chapter 6, since that's not as far as we get in homework number 6. So we'll have to figure that out. Exam number 2, did I say the right exam? So exam number 2 should cover from exam 1 up to homework number 6 and maybe a little bit beyond. Hopefully the Graham-Schmidt we can allow for exam number 2. But that's about as far into chapter 6 as we will cover. Today I hope to finish chapter 6, which takes us into minimization problems. And if you didn't go over the notes from last time, you might look at the last paragraph or page where I wrote down after class this way of implementing this projection onto a subspace or a subset within your overall linear vector space V. We'll use that to talk about a minimization problem using these inner products. Then we will look at a new entity, linear functionals. Inner product takes how many pieces of information? 2. It takes 2 vectors to spit out a scalar. A linear functional takes 1 vector and produces a scalar. We need this idea of a linear functional to talk about adjoints. And adjoints will allow us to move into chapter 7. Adjoints are another function, and they're sort of dual to our map, linear map T. And we'll hopefully start to appreciate or understand that a little bit more by the end of today's lecture. Let's then get started with these minimization problems, or a discussion of such. And we'll start by saying we often run into problems or we might identify problems. Maybe we don't run into them. Maybe we have to find them. We have to discover these problems. We often have problems that can be cast in the following form. We might be given U, which let's say is now a subspace, of the underlying vector space V. And maybe we are given a vector in that underlying vector space V. What we want to do is actually find a U in the subspace that's close to V. How close? We want it to be as close as we can get it. We want to minimize the distance between a vector in the subspace U and this vector V. And if you're trying to visualize this, you might be thinking about a three-dimensional vector, and now you want to project that down onto the xy plane, for example. That's really all we're trying to say here. So given a subspace U in this underlying vector space V, and given a vector V in the subspace, or inner product space actually V, find, so now we want to find U, a vector in the subspace capital U, such that the norm of V minus U is as small as possible or is minimized. That's the minimization problem. Or another way of saying that is we want to find this vector U that is closest to V, and remembering that we have to stay in the subspace capital U with our U. To do that, really all we are going to do, it's a big all, but what we can do to meet that or to achieve that goal is to simply project V orthogonally onto the subspace U. Orthogonal projection gives us, let's say, just the tool to achieve the above minimization. Part of that is cataloged in Proposition 36 in Chapter 6, which states if U is a subspace of V, and we have a vector that belongs to V, then V minus P sub U of V, that's the projection operator applied to the vector V, and the difference between V and this projected object onto the subspace U is always less than or equal to the distance from, or the norm between V and U for all the different U in the subspace capital U. Meaning you give me a U in the subspace, And I'll compare the distance from V to that U, and that distance is going to be bigger than the vector V to where we would orthogonally project V into U. Is that making sense? So if we're on the XY plane, let's say we're in, well, we'll get to that in a minute, but this is now saying that the orthogonal projection of V into U minimizes the distance. That's really all this is saying. And that's said here. Also, if we have equality, meaning if you stumble upon the U that makes that inequality an equality, then that U is in fact the projection of V, orthogonal projection of V onto that subspace capital U. Let's see where that, or how we can demonstrate that or show that or prove it. Let's say that we are now given a U in the subspace capital U. Then it's possible to look at, V, the norm of V minus projection operator into U of V, let's say that's squared, that's less than or equal to itself. Let me just write this down. That's actually equal, but I'm going to add a little bit more to that. Let me add another vector, which is U minus projection of U. I'm sorry. Let me rewrite that so that it will come out nice later. P sub U of V minus U squared. Is it clear that I have that inequality? I'm just saying A is less than or equal to A plus an epsilon is really all I'm saying, where epsilon is always non-negative. That's all I've said in that statement. But let's look at what happens inside these norms. Where does this result or vector live? V minus the orthogonal projection of V onto the subspace U. So now we have, basically, we've decomposed our V into two pieces, haven't we? A piece that's the subspace U and pieces that are orthogonal to that. What I would like to think is these vectors are in one of those two places. This one we now say V minus something. Where is this P sub U of V living? P sub U of V is a projection of V onto the subspace U. So now we take a vector that's in U and we subtract that from V. Where is that vector living? U perp, isn't it? It's in the orthogonal subspace, so this now belongs to U perp. Where does this vector live or belong? It's in big U, isn't it? The subspace U. This one is an element of big U. Because we've projected V onto that subspace, and then we've subtracted another vector, little u, from that vector that's already in U. And we know that that is a subspace, so they stay. It's closed under addition. We now have a vector that's in U perp and a vector that's in U. Those are orthogonal to each other, which allows us to apply some theorem that begins the Penrose book in chapter 2. Do you remember what I was talking about was the beginning of chapter 2 in Penrose? Some theorem, Pythagorean theorem. We can now apply the Pythagorean theorem. So really, I should be saying this is now equal to something, but since I want to just write it underneath, I'm going to say less than or equal to. Is that okay? This is now less than or equal to. So if this is a squared plus b squared, then that's equal to c squared, because we can use Pythagorean theorem, and c squared is just a plus b. So now we have a, which is v minus p sub u of v, that's a, plus b, p sub u of v minus u squared. This is simply this particular connection is the Pythagorean theorem. Is that okay? This was just basically a, this was b, and this is c, which is a plus b. So a squared plus b squared is equal to c squared. Because they're orthogonal, we can do that. We don't have this sort of cross piece. That's not 2 to the b. Getting to be or not to be, no, we aren't Shakespeare today. Sorry. Where was I? I know where I'm at. I don't want that there. So I'm going to now make that there. How's that? Okay. Well, what does that red C actually become? The result that we want, isn't it? The minus p sub uv plus the p sub uv is the same, so that we can now say that this is less than or equal to v minus, u squared. And that's actually what we set out to show. That we wanted for any u in our subspace, we wanted to show that v minus, the orthogonal projection of v into the subspace u, is as small as we can get in terms of distance. And we now have shown that. And as I have indicated before, we can think of this geometrically. The geometric interpretation is saying if we now have this, let's say, vector v, maybe it's sitting off here from the origin, so that we now are going here, and now somebody says, oh, but I have a subspace u that's there. Then what we are doing is we are projecting that v orthogonally onto u. So this green line represents the subspace u. And this point right here is now the projection of v onto u. And that is, in fact, the closest point in our subspace u to v. And this dashed line, right here, it belongs to the perpendicular the orthogonal complement, or the perp, of the subspace u. That's the visual, and that's just in 2 dimensions. We can do this in a more general finite dimensional space. That's what we have in terms of the possibility exists to find this minimization or this minimal vector u. Now we simply have to worry about creating this projection operator. If we can do that, then we've solved minimization problems. And that's where I want to rely on you going back and looking at that last paragraph in last lecture, which was dealing with how do we do this orthogonal projection onto a subspace? How do we generate this piece of u of v? So the solution of general minimization problem is to actually take u equal to p sub u of v. Which is the orthogonal projection of v onto this subspace u, which is contained in v. And we can connect that with what we've done. But earlier we saw if we had an orthonormal basis on U, the subspace, let's say, for example, e.g., maybe we now have this list E1, E2 up to E sub m. What are we then saying about the subspace U dimensionally? E1, E2 up to E sub Michigan is an orthonormal basis. So the dimension of U is Michigan, isn't it? It's M. If these vectors are orthonormal and they form a basis. So they span the entire subspace, capital U, and they're linearly independent. And they have length of 1. If we have such a basis, then from equation 635, which is what I did after lecture last time, I just wrote it down from what we were talking about, we can build or create this orthogonal projection of V onto the subspace U by looking at the inner product of V with the first basis vector E1 and finding it's the component of that, and then scaling E1 by that component. Then take the inner product of V with the second orthonormal vector. That gives us a component in the direction of E sub 2, and scale E sub 2 with that value or that scalar, and we just keep going until we've found all inner products with V and the M orthonormal basis vectors. That's basically our minimization. Here's the strategy. Now you can do all sorts of minimization problems. The solution comes down to finding orthonormal basis on this subspace U, and then computing a bunch of inner products, and then computing inner products, for example, using equation 635 structure. So we get all these inner products and we put them together using equation 635, and there is our vector U that minimizes that distance between V and some vector in our subspace U. One example that's a good one that we won't talk about in class, I'm just going to direct you to it, is another way of approximating sine of x. You've probably looked at approximating the sine of x using somebody's expansion, blank expansion, a Taylor series. And you could truncate that at a certain power of your polynomial. Something x cubed, x to the fifth. Well, here in the textbook, you'll want to look at this, and it's pictures. So you can look at these figures to compare the Taylor series expansion with a fifth order polynomial and another polynomial that's fifth order, and just see the difference or the errors that exist between the Taylor series and this approach to finding a fifth order polynomial that minimizes the distance between a function, sine of x, and a fifth order polynomial. Axler has a great example involving finding a polynomial approximation to the sine of x. That if we think of sine of x, what is it in terms of where does it live in terms of the dimension of its space? It's not really a finite dimensional space, is it, that the sine of x? It's in some infinite dimensional space or a function space, but we're actually approximating it with a fifth order polynomial. And you can still do that because all of these techniques just rely on capital U, the subspace, being finite dimensional. It didn't really say where V is living. V can actually live in an infinite dimensional space, so we won't usually deal with those kinds of minimizations in this class, but it's possible. This actually takes place in function space, which is where the original V vector lives. But you are now at the maturity level, now that we're in chapter 6 of this book, that you can understand it. There's the first goal of our class for today, is minimization. Now, a lot of problems can be solved by doing a minimization problem, and you're now capable of understanding an approach to doing that by playing with some of these concepts of linear algebra. Let's now introduce a new object called a linear functional, and we'll put that under the heading of linear functionals. A linear functional on a inner product space, capital V, is a linear map between the inner product space V and the scalars. If we pick a vector W in this inner product space V, then the inner product of a arbitrary vector in our vector space V with this specific vector W is actually a linear functional. Meaning you can now pick any generic vector W and just keep it fixed. Keeping it fixed and then looking at any other vector V, little v, in your inner product space capital V, now you've got a linear functional. It'll produce a scalar when you compute this inner product, and that's what a linear functional is doing. It's trying to take a single vector in your inner product space, capital V, and produce a scalar. You can do that using this inner product with some vector W. And we've already been using that. We already saw that this inner product is a linear map to the scalars. It's just we didn't give it this specific name before. Now we can call it a linear functional. What's surprising or interesting or nice is that for any linear functional, let's call it phi, on our inner product space V, we can actually pick a vector W in the inner product space V such that we can duplicate the application of this linear functional phi on V, or we can set it equal to the inner product of V with this vector W that we would have to find, but we can find such a W. So given a linear functional phi, just some generic linear functional, then it's possible to find a W that will provide us with a way of generating that same linear functional with this inner product. And that gives us a theorem. Theorem 45 says, given phi which let's say is a linear functional on V, then there is a unique vector W that belongs to V, the inner product space, such that phi sub u, or this linear functional applied to a vector u, can be set equal to or is equal or equivalent to the inner product of u with this unique vector w for every one of these vectors u in the inner product space V. So I'm using u instead of maybe little v. I could have said phi sub little v, or the linear functional applied to another vector little v that belongs to the inner product space, but I think in the textbook in Theorem 645 he switched to using u. But it's now just any vector in your inner product space can be, or you can find a unique vector w such that the inner product of the original vector with that w is equivalent to the linear functional phi applied to that vector u. Yes? So the question is there a w? It's basically there is a fixed, so I should try to repeat the question before I answer it. The question was, every time, or did you ask for each u, is there a different w? So is there a different w for each u? No, there's actually a unique w for each phi, and that's true for any vector v or u in the inner product space V. Is that making sense? So if somebody gives you a linear functional phi, and that may be some really mixed up thing, but it now generates a scalar for every vector in your inner product space V. Whatever that produces, you can actually find for that person a unique w such that now all you have to do is form the inner product with w and whatever vector somebody gives you in the inner product space V. Does that help answer your question? So let's see if we can show this, or can we figure out the w? Can we find such a w? And is it unique? Yes. So it is important that it's a linear functional. The question is it important that it's a linear functional? And yes, it is, because we're going to be using that to prove this theorem. So that condition that it's a linear functional, that phi is important in the proof of this, that we can show that we can find a unique w that will generate the same scalar when that linear functional is applied to any vector u in our inner product space, capital V. Okay? So phi is, well, what do we mean by a linear function? Well, you can think in those terms, but it now needs to be, what are some properties of something being linear? So now it has to have additivity, doesn't it? And homogeneity. So as long as a linear combination of a set of vectors can be generated that is the same or consistent with the sum of that linear combination. So it's a linear operation. is what we mean by a linear functional. Okay? So now let's see if we can show this, that it's true, and the process of showing this will actually produce this W that we need. Here's our proof. So now let's take an orthonormal basis on our inner product space, capital V. And let's just call that E sub 1, E sub 2, up to Nevada. This is now an orthonormal basis on the entire, well, it's a basis. So, and it's on our inner product space, capital V. Not a subspace, but it's on the whole thing. Let E1, E2, E sub n be an orthonormal basis on capital V. Then, if we have this linear functional applied to a generic vector u, then we can say that that phi is operating on u. We put a u into this machine. This machine is a linear functional. It's going to generate a scalar. So we plop this vector into phi, and out comes a scalar. And it's a linear operation. But now let's be creative, not so creative, but let's just rewrite u in terms of this orthonormal basis. And we know how to do that. We just project the component of u on E1 and use that to scale E1. So we're now going to do an orthogonal decomposition of this arbitrary vector u in the inner product space, capital V, which says that we take the inner product of u with E1 and use that to scale E1, plus u E2's inner product, E sub 2, all the way u inner product with E sub n and E sub n. This is just u. It's an orthonormal decomposition of u. Yes, so this is phi of u. Is that okay? So the question was, what is this phi sub u? That's just a shorthand of saying this linear functional phi is applied to some vector u, and this some vector is any vector in our inner product space, capital V. Yes, so now we have an n-dimensional vector u, and we're mapping that to a scalar. A scalar is one dimension, well, yes. But remember, a complex number, you can think, but that's one-dimensional in the complex field, right? But it could be a complex scalar. Are we okay with that? Now, what do all of these pieces look like, or what are they? What is this? What is this? And what is this? All the e's, the e sub 1, the e sub 2, the e sub n's, those are vectors. But those inner products are scalars, aren't they? These are scalars. So that if I wanted to, I could now, what? Because phi is linear, I can now apply this additivity property of phi, or homogeneity property. It's both, really. I'm looking at the additivity, so I now look at phi applied to the first piece, and homogeneity, I can now slide that scalar out of phi. And I'll do that then now. So here, I'm going to say that's equal to, and if you allow me, I'm going to sort of use that maybe abusive notation of now phi sub u to mean phi operating on some vector. Meaning I can now say u of e1, that's just a scalar, phi sub e1, plus u e sub 2, that's just a scalar, and it's scaling this linear functional applied to e sub 2. And e sub 1, e sub 2, these are just n-dimensional vectors. They're orthonormal in our inner product space V, but we can plug those into this machine that's phi, that generates a scalar. So now e sub 1 and e sub 2 are being used in these inner products, and what is that inner product outside of the very first one doing? It's now projecting u, or it's saying how correlated or how aligned is u with e sub 1. The amount of alignment will give you the size of that scalar. If they are strongly aligned, u with e sub 1, then that inner product will give you a nice big number. If they aren't very aligned, if they were orthogonal, that inner product would give you a 0, and that would say you have no, or u is not in the direction of e sub 1. Is that clear? And we just keep doing this. We have all n of these to do, but is it clear what we've done? We've now used linearity to sort of slide that phi through, and now I have n of these pieces that are scaled by this inner product. So that I can now say I have u e sub n, phi e sub n. And this is simply using the linearity property of the functional, which is what somebody asked before. Is it important that it's linear? Yes, that's where we've used that condition in our theorem. Is that clear? So we're using that to basically do this first step in our theorem. Now what do we do? Well, if we remember what we have a lot of things going on. This, and this now are what? Scalars again, aren't they? So these are now scalars. Those are just numbers because that's that linear functional applied to n, little n different vectors. And if we have a scalar that's outside of an inner product, we can actually slide it into that inner product. And if I put it into the second slot, how does it come in to that inner product? What do I have to do? I have to conjugate that guy, don't I? That scalar. So now if I slide those phis into the inner product, because of the conjugate homogeneity of the second slot, I can put those in with just conjugating that scalar. Whatever phi sub e1 generated, I conjugate it, and now I can move it in to scale e sub 1. Do you see what I'm trying to do, maybe? I'm trying to build this w. I want to somehow end up with something with w and u sitting in the first slot of my inner product. And then I've created what I said I wanted to create. Where was I? Trying to do a second slot. Move that scalar into the second slot. I now can say this is equal to u phi sub e1 conjugate e1 plus, or maybe I should make it more clear, phi sub e sub 2 conjugate e sub 2. Is it clear what I'm doing? And I just keep doing that. I now have u phi sub e sub n conjugate e sub n. And that result was due to the conjugate homogeneity of the second slot. And now what I want to do is I want to just end up with one inner product. And I can do that because of the additivity of my inner product. I can now collapse all of those, and now my second slot term is going to be huge, but it's just a vector. Bless you. So now I can put all of this into one inner product. I can say that's equal to u and a new vector, phi sub e1 conjugated e1 plus phi e sub 2 conjugated e sub 2, etc., phi sub e sub n conjugated e sub n. And that was possible because of the additivity of the second slot. That clear? So that this, whoops, I messed up. I put a curly brace in there and I forgot to close that curly brace. So when I was compiling that, it gave me an error. So that now I need to close that curly brace, and then I can close the right bracket. Meaning now everything in that curly brace is this vector w that I was trying to generate. So now phi sub u can be written as u w with w equal to phi sub e1 star e1 plus phi sub e sub 2 conjugated e sub 2, etc., phi sub e sub n star e sub n. So, yes? So now the question was, it seems that the linear functional is sparsely defined. I'm repeating the question, I think. How do we know that W is unique? That's exactly where I was going. Great question. He's a plant, I know. No, I didn't set that up, but that's actually the right question to be asking. Can we show that W is unique? As long as we have a linear functional phi that we can, it's now a machine, we just have to throw vectors into it and it will generate scalars. This now gives us a procedure, except what does that depend on? That procedure just depends on having an orthonormal basis on our inner product space, capital V. If we can build that, and we can do that with Graham-Schmidt, can't we? Then we can do this minimization problem. I'm sorry, we can do this creation of a linear functional as an inner product. So now let's see if, I hope then that it's okay that we can say a W exists. The question was, is that W unique? Which is what the theorem says. So now let's assume that we can actually find two W's that produce the same phi sub u. Let's now say that phi sub u is equal to u w1, and it's also equal to u w sub 2 for all vectors u. Now we just need to show that w1 is equal to w2. Well, if phi sub u is equal to the middle and the right, why don't we just compare the middle and the right, or subtract them? And if they're equal, they should give us the zero vector, which is really just a zero scalar in this case, since those inner products produce a scalar. We now can say that 0, a scalar, is u inner product with w1 minus u inner product with w2. And that's true for all u. That's how w1 and w sub 2 were defined. They were equal to the same thing. So now we're just subtracting those. We have phi sub u minus phi sub u, and that's 0. Well, now we can play with the inner product. We can play with the additivity of the second slot, meaning we now can say that u, comma, w1 minus w sub 2 is equal to 0 for all u. But now let's get creative with the u that we pick. This is true for all u. Then it must be true for a particular u, and the particular u that I want to select is w1 minus w sub 2. So now if I'm creative with the choice of u, this is true for all u, and u is anywhere in our inner product space. Let's just let it be. The Beatles didn't start, did it? Let's just let that vector be w sub 1 minus w sub 2. So now if we therefore consider a particular u, and that particular u, let's let that be w sub 1 minus w sub 2. Now we have w1 minus w sub 2 inner product with w1 minus w sub 2 equaling 0. But by the definiteness property of the inner product, we know that that forces the things in the slot to be 0. The only way that we can get 0 is for the slots to be 0. So but the definiteness property of the inner product says the inner product of A with itself is equal to 0 if and only if A is actually the 0 vector. In our case, A is actually w1 minus w sub 2, and that's now equal to 0, which says that w1 is equal to w sub 2. Therefore, w is unique. So we found that it exists and it is unique, and that's then enough for the completion of that proof. Is that okay? Does that help you feel a little bit better or more comfortable with that? Now you are given a linear functional. You can now find a vector w that you can form an inner product with any vector in the inner product space to generate the same scalar as that linear functional. And you know now how to build that w, how to find that w. Now that leads us into the next topic that's going to be important in Chapter 7, which is the adjoint. But to talk about the adjoint, we actually need, and there's two different adjoints floating around in linear algebra. This is one and it's not the other. So stay tuned to the Sesame Street song, but this is one and they're not the same, okay? These are not the same adjoints. This is one particular choice or use of the word adjoint. But to play with this term now, we actually need two different inner product spaces to talk about this adjoint operate. Well, we will in chapter 7 turn it into an operator, which now means we have to go back into the same space that we started in. Now we're going to just say we don't need to specialize that adjoint property. Now let's say that we have T is a linear map from V to W. We now have vectors little v living in capital V and vectors little w, the result in the codomain, living in capital W. And we need an inner product space for these vectors V, and we need another inner product space for the vectors in W. And V and W are both finite dimensional inner product spaces over the field F, where F could be the real numbers or the complex numbers. So if we're given a linear map from V to W, we're mapping now because V and W aren't necessarily the same. We now have a linear map T. Then, maybe I should go back to where I started with the if and color-wise. Then a new object, T dagger, that's a dagger as the superscript, T dagger, which is the adjoint, and that notation is a little bit different than the textbook. In the textbook, he actually uses what we're using for the complex conjugate. Okay? So hopefully it's clear from who's talking what we're doing. The adjoint for our lectures will be this dagger. So then the adjoint is a map from W to V defined by the following construction. So first, we pick a vector in W, which is in the codomain of our original linear map, capital T. Then given a linear functional phi on V such that phi sub V is equal to TVW, and now remember what all of these players are doing or where they live. This inner product is made up of vectors living where? They're all in the codomain, aren't they? In capital W. These are vectors in W. Little w is obviously in W, but T, the linear map, was taking vectors in capital V and mapping them into W. The first slot is in W, capital W, and the second slot is in the codomain, capital W. Now remember, little v is in V, so that's what I just said, but T is this linear map from phi to W, which says that TV is in the codomain. So now given a linear functional on V such that phi sub V is equal to TV comma W, then this is how we define the adjoint. The adjoint applied to W is the vector in capital V such that phi sub V is equal to V T dagger W. And again, where are these guys? Those are in capital V, aren't they? These are vectors in V for the same argument before. All of that then implies that T and its adjoint, T dagger, are defined such that these scalars are the same, where the scalars are TVW is equal to V T dagger W. That's how we're defining T dagger. So let's look at an example and see if if we can make sense of this. So this is now creating or building an adjoint. Let's start with a linear map T in R3 and going to R2. So we're dealing with real fields, and a three-dimensional vector is our domain, and that gets mapped in a two-dimensional codomain, and let's say that it now gives rise to x sub 2 plus 3x sub 3 comma 2x sub 1. We start with a 3 vector and it maps into a 2 vector in this way, and T is a linear map. T dagger then must map from what to what? T goes from 3 to 2. T needs to go from 2 to 3, doesn't it? Now, we need to create that T dagger. To create the adjoint, T dagger, we pick a vector W in capital W. So now to follow the notation, and this is in the book, to follow the notation in the book, let's call W some y's. Y sub 1, Y sub 2, and that's obviously in R2. Y1 and Y2 are just real numbers. We want then V T dagger of W, we want that to be the same scalar as T V W for our choice of W and V. This now says that V we were just calling x1, x2, x3, and that's going to then be inner product with T dagger W. But W was y1, y2. This is just our v. And we want that to equal TV W, which is y1, y2. But what is all of this? T applied to V, we said was a 2-vector, and it was a 2-vector that looked like x sub 2 plus 3x sub 3, comma, 2x sub 1. That was how we did the linear map from V into its codomain. Is that okay? Now let's form the inner product of that using the Euclidean inner product, which says that we now have the first components in the 2 slots combined and the second slots multiplied together. That's just the Euclidean inner product. But we really want that to start looking like x1, x2, x3 scaling something. So let's now sort of multiply that out. We have x2, y1 plus 3x sub 3, y1 plus 2x1, y2. We want that to actually equal, boy, I'm sorry for the time, x1, x2, x sub 3, t dagger, y1, y sub 2. But if we look at that, we have 2x1, y sub 2. So we're trying to find what in x1 needs to be, how does x1 need to be scaled? Let's now look at the next piece, which is x sub 2, and that was x sub 2, y1, plus x sub 3 was in there with a scaling of 3, y sub 1. So now we know how x1 and x2 and x3 are put together to produce basically T dagger, so that we now have, this is now x1, x sub 2, x sub 3, which is just V, scaling by what? x1 is scaled by 2y sub 2, x sub 2 is scaled by y1, and x sub 3 is scaled by 3y sub 1. If we compare pieces in the different slots, T dagger of Y, T dagger of W, which was T dagger of Y1, Y2, is going to produce a 3-vector, and that right-hand side is our W, isn't it? Or I'm sorry, our V, which is now 2, Y2, Y sub 1, 3y sub 1. And that's now our dagger map, which is a map from 2 space into 3 space. You give me a 2-dimensional vector, y sub 1, y sub 2, T dagger will produce a 3-vector in this particular manner, such that it's now the adjoint of our original linear map T. That's chapter 6. Thank you for being patient. We'll pick up using that in, well, maybe we'll do a little bit more 6 before we get into 7.